Thank you, everybody. I'm Gabriele Paoloni. I work for Intel as a lead software architect for functional safety system. And I'm currently leading the safety architecture working group in ELISA. That, from what you have seen in the previous session, is one of the main working group of this project. Okay. So the agenda. So first we'll give some newcomer introduction. Then we will review the objectives from the last quarter. We will go over and summarize the activities of the past 3 months. Then we will move to the objectives for the next 3 months, and then at the end we will take question and answers. Okay, so newcomers introduction. So the Safety Architecture Working Group, it kicked off at the 3rd ELISA workshop now some time ago, early in 2020. The working group description. So according to technical safety requirements produced by domain-specific working groups, the focus of the Safety Architecture Work Group is to determine critical Linux subsystems and components in supporting safety functions, define associated safety requirements and scalable architectural assumption, deliver corresponding safety analysis for their individual qualification and their integration into the safety critical system. Now, understand this is a bit cryptic, so for newcomers, please hold on, and it will be more clear as we walk through the slides. Okay. Weekly meeting. We meet via Zoom every Tuesday. Everybody is welcome to join, and if you wish to do so, you can follow the instruction that you can also find in this deck. And all the working group material can be found at the Google Drive directory that is pasted here. Okay. Right. The scope. Now, in order to explain the scope of the working group, and therefore, to expand a bit better on the cryptic sentence from the previous slide, I'm using this work in progress document. Okay, the entire document, you can find the link at the bottom. Okay, so as you can see, if we take a standard product life cycle, okay, the one that you can find in any safety standard as well, our working group is mainly focused in the yellow box that you can see on the right. Okay, so it works mainly on the activities of safety requirements definition, software architectural design, specification, and safety analysis. Okay, this is where the main focus is. So therefore, what we do in practice is, the first activity is to process the technical safety concept from domain-specific working group, like for example the automotive working group. Then we do an initial partitioning and classification of the kernel on the basis of the elicited requirements. So practically speaking, what we do, we try to partition the kernel between what we can tell is safety relevant and what is not safety relevant. Then we derive safety analysis to confirm and derive a safety requirement for all the safety relevant kernel components that support the safety function. And also, we try to figure out what are the best set of config parameters in the context of this specific safety analysis. Okay, and as well, we try, to improve the architectural document as part of this safety analysis. So, for example, like kernel doc headers. And the last goal is, to drive to justify freedom from interference between safety relevant and non-safety relevant application, as well as safety relevant and non-safety relevant kernel components. Okay, and so to identify, the critical kernel components guaranteeing the integrity of the safety application and the main interference point between safety relevant and non-safety relevant kernel elements. Okay, so this is, this from a high-level point of view, it summarizes what is our focus as a working group. Okay, and in the next slides we will see a summary of what we have done in practice. Okay, any questions so far? Okay. Working group goals that we set in the last workshop. So in the last workshop, we wanted to complete the top level kernel safety requirement and associated entry point identification using the mind map and code tag model. Now, this is, we have completed the definition of the kernel safety requirement. However, we have not used the mind map and code tag model because we actually focused more on the safety analysis, on the definition of a qualification approach, and we are still so we're still working effectively to find a best the best tool for the architectural representation. Okay. However, the definition of the kernel safety requirement that is completed with respect to the Telltale use case, okay, or almost complete. Also, we started the safety analysis for the Telltale safety application. Yes. Then we set as a goal consolidation and refinement of the qualification methodology using the Telltale use case as a driver. So this is yellow because we, like in the last couple of months, we came up with a proposal that you also will see later on in the deck. It is a sort of innovative qualification approach for Linux to be used in safety critical application, and we are currently working to evaluate the feasibility, to evaluate the applicability to Linux. So this is really a work in progress. And the last point, this is red because we have not started it yet. Start the freedom from interference, considering also the non-safety relevant user space process. So this is something that we still need to look into, and the reason why we still need to do this is because we mainly worked on what is yellow, so on this approach to qualify the safety relevant code of Linux, and we will take the last bullet as a next step affected. So if we can go a bit more in detail. So this is a picture that depicts, from a high-level point of view, what we've been working on. So this is the diagram of the Telltale safety application that Johan will explain better in the next session. Okay. So with respect to the Telltale use case, what we had to do, we had to define kernel safety requirement associated to the technical safety requirement of this use case. Okay. And also we had to associate a kernel entry point to this kernel safety requirement, and also, as we have to feed back to the automotive working group for the refinement of the safety concept. And yeah, so with respect to this activity, so this is a very quick snapshot of the kernel safety requirement of the Telltale use case. You can see that on the left we have the unique ID of the technical safety requirement from the safety concept. We have an ID for the kernel safety requirement, a title, the description of the requirement itself, and on the right we have the entry point of Linux that is associated to the Linux component that is actually supporting that safety requirement. Okay, and this is what we used, to initiate the safety analysis of Linux. Now, okay, so before we present an overview of the architectural model and of the safety analysis, so we need to take a sort of break, as in, so what we did, we introduced a sort of an innovative qualification approach that will be explained better tomorrow. So tomorrow there will be a dedicated session for this, okay? And please join this session if you are interested. So this approach is, the reason why we applied this approach is because following the standard Part 6 approach, the effort, to reverse engineer all the single kernel function and to provide all the required collateral, it's too heavy, okay? And therefore we came up with this, with a sort of trade-off where we identify single Linux blocks or components, okay? So the kernel is divided into software block, and each block is qualified according to the part 8.12 of the ISO 26262, and then we have the integration of the different blocks that follow the ISO 26262 part 6. You can see where is the the delineation mark here, right? So we have safety architectural design, down to the safety architectural design, we follow the part 6. Then we have part 8.12 for the specification and testing of the different blocks, and then we have again the integration and app is done according to the part 6. Okay, I think there are 2 questions. Where to download the presentation so I can follow the link? Yes, will be provided after the workshop. Thanks. Okay. Okay, let me take. Okay, I'll take all the question after the presentation. I want to make sure that I go down at the end of the presentation, and then I will take the question if that is okay. 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 So Telltale kernel safety analysis. So as I said, we focused on the Telltale use case. And with respect to this use case, we focus on the ioctl syscall. So the ioctl is used to set the timeout of the watchdog, okay? And then accordingly, we defined the software architectural design and the software block specification for the ioctl. And we derived a safety analysis based on this architectural representation and based on the block specification, okay? And finally, also there was an interesting FTA fault-free analysis approach that was introduced, okay, to complement the FMEA and to verify the architecture and design documentation of both. And yeah, and so this is where we are right now in summary, okay? Now, to give you an idea of what we mean by software architectural design and software block specification, I have a few snapshots here. So you can see that, so software architectural design, okay, so we have basically partitioned the Linux, okay, and in order to do an initial partitioning, we use the maintainer file. So this will, this will be presented also tomorrow, okay? And we derived this communication diagram between the target file system, that the target subsystem, that in our case is the file system, and all the other subsystem driver that it communicates with, okay? So you can see that here we have the ioctl syscall input, okay? And you can see these are all, the functions that are invoked to communicate with other subsystem in the context of the ioctl scenario, okay? And finally, this is the unlocked ioctl that is, invoked to set the timeout for the watchdog, okay? And this is a communication diagram. We also have a sequence diagram to show the dynamic behavior. And you can see, again, this is the file system is the target subsystem here, okay? And you can follow here all the sequence of events, okay? And this is, to provide a software architectural design representation compliant, with the part 6, okay? When it comes down to the block unit specification, what we did, we wrote in natural language the specification for the ioctl. So this is an header, so a kernel doc header that is meant to be, pushed into the code, okay? That has been discussed, and proposed, not yet to the Linux mainline, indeed. But the idea will be, you can see here that the idea will be to provide in natural language the specification of this API to explain what is the expected behavior, okay? And the idea is, to be able to write a test out of this specification in order to make sure that this block with respect to this function behaves as expected, okay? And you can follow the link, to look at the details if you want, to join the discussion, the working group, or to come, with the detailed questions, okay? And finally, we have the safety analysis. So based on the architectural design and based on the block specification, we have identified the failure modes, okay, and that have been used to refine safety requirements, and also they are also used to identify what are the most sensible and part of the code supporting this specific ioctl scenario. Okay. And the last but not least, tools. All the diagrams that you saw that I presented, these are done and produced by hand. Okay. Indeed, this is not very sustainable. You know, it's a bit heavy, you know, to write all these diagrams by hand. And in parallel, we are working on tools to support the architectural modeling of Linux. As a first step, we released a call tree tool, and you can follow the link to look at the tool. So this tool is basically, it allows to derive statically a tree of call, of function calls that departs from you know, a specific API of Linux. Okay. On the right, for example, I'm showing you know, all the tree of departing call from panic. Okay. So this is indeed this is not complete. Okay, so this is just a snapshot of the call tree. Okay, and why this tool? It's important because it helps with the generation and verification of the software architecture design diagrams, more specifically with the communication diagram. Okay, and right now we are working, you know, for a tool for the automatic generation of communication diagrams. Okay. Goals for the next 3 months. First goal is to complete the software architecture design and the safety analysis of the Telltale use case. We need to start the freedom from interference, considering non-safety relevant user space processes and non-safety relevant kernel code. We need to develop and release tools to enhance the support, the generation of software architecture design documentation for the hybrid approach. We need to introduce runtime verification monitor to support the integration of safety critical Linux kernel blocks. You will see an introduction about runtime verification monitors tomorrow in a dedicated session. Okay, and also we need to evaluate the going high scale with the hybrid approach. So effectively, if this approach turns to be valid and we get on a consensus from a safety point of view, we need to evaluate what it means to you know, to go high scale with this. And just a note here. All the discussion about you know, the safety the safety validity of this hybrid approach and the, you know, and the how to apply it to Linux, this will be moved to the development process working group. Okay, because it is a more with respect, I mean, it's more in the scope of the development process working group, right? So here we should focus more on the analysis of specific use cases. Okay, so, and in order that, you know, so I mean, we introduced this hybrid approach here, but from now on it will be moved to the development process working group. Okay, so now question time. I saw the chat is being quite active. So the first question was from Sunita. Safety feature implementation is usually very much platform specification. How do we plan to have common design specification to support all platform? Like if the Telltale rendering or sham or LVC fail any reason, kernel hang and crash, then it's been taken care by either hardware or other RTOS. Okay, a good question. So Sunita, yes, the idea here is, so if, the specification of the hybrid approach are done in a way that is context independent, or better. So let's say the hybrid approach itself can be applied also to a safety element out of context. Okay, and in fact, if you join the session about the watchdog, you will see that we have taken a safety element out of context approach to start qualifying the watchdog accordingly. And then we linked the qualification of the watchdog in a specific context of use, that is the Telltale use case, okay? But generally speaking, what we are trying to do here is we are trying to first look, into a specific example, like the Telltale use case, trying to derive a methodology that can scale later on also to more complex use cases or to safety element out of context, so that effectively then we can, we can scale it. Did I answer your question, Sunita? You can unmute if you like.
Yes.
Okay, thank you. Interesting investigation reminds me of the early days of the SID to Linux MP project until we realized it's not a risk mitigation. Okay, yeah, well, I was not aware that this hybrid approach was already considered in the SID to Linux MP. So Lucas, yeah, if you want to, to provide the material showing, that this is not a valid approach, you're welcome. Alessandro, can you comment more on the basic advantage of so-called hybrid approach using software qualification approach on the lower part of the V model and its linking to open source development model? We have 3 minutes left. I mean, the advantages is that indeed, applying the hybrid approach, you don't need to produce all the collaterals that will be required for all the single units. When by unit we mean the single function of Linux. Okay, so effectively we can focus on the API that on the incoming, and outgoing API of the different blocks. Okay, so that would reduce the amount of collaterals that we need to maintain. And how it links to open source development model, it will be clear probably. I think if you attend tomorrow's sessions, you will have even more details about this. Okay. Which automotive safety integrity level are we targeting? For the Telltale use case, we targeted ASIL B. Now, however, we don't have like a specific goal, as in we are trying to evaluate what we can do, and then obviously we'll have discussion maybe on what is likely to be targeted by using a specific qualification approach. Okay. Right now, practically speaking, we are evaluating an ASIL-B with the Telltale use case. Tomorrow, I don't know. We can also try to target the different ASILs. Okay. So yeah, this is where we are now. Okay, so we are at the top of the hour, and if there are no more comments, I would close the session for the next one.
One last question maybe. So are we targeting like exceptions and interrupts of different categories as a software unit?
Different categories? You mean different ASIL?
Yeah, means the networking, interrupts coming in, or the storage related things coming in. So we have got the various K threads, kernel threads, and so on. So are we planning to analyze them from the safety perspective?
Are we targeting? Yes, I mean, we are, we target, I mean, every use case has different subsystems, okay, supporting the safety relevant application, okay. So we are starting from the Telltale, and then therefore we are focusing on specific ones, but as we move, you know, to more complex use cases, probably, yeah, we'll also touch on the qualification of other safety relevant subsystems, okay? So, but if, I mean, as I said before, the interaction between non-safety relevant and safety relevant, so the freedom from interference, this is something that we still need to look at, okay? And we need to explore.
Okay. Okay. Thank you.
Yeah. Okay. Thanks, Lucas, for the good luck. As I said, if you have already material available, please share. Okay. Thank you.